Now, this is power. Tell me, what's the difference between power and energy? Has this got an idea? Malika.
I think like power, you can like start and like turn on and off, but then energy, like it's always there.
Energy's always there. The power you can turn on and off. Okay, that's okay. Yeah, Gemma.
Is it like power's energy over time?
Power is energy over time. So the difference between power and energy is energy doesn't care about the time. It doesn't matter how long it took to do that work or create that energy. Not create, but change, transform that energy. But power is how much energy is transformed in a given time. So Senna, difference between power and energy in one word. Don't tell her. She's not paying attention. She needs to be.
I don't know either.
Put your hand up if you know the word. Hasti. Yeah. No, you don't know? But you put your hand up. She's like, ah. Sam K.
The word is time.
Time. Senna, difference between power and energy in one word. Time. Good. So, who here likes sports cars? Ethan likes sports cars. Ethan, what's your favorite car?
Alfa Romeo.
Alfa Romeo. Okay, so Ethan gets, he's like, gets a job at SpaceX or something. He's gonna buy an Alfa Romeo. What color?
Red.
Red. A red Alfa Romeo. Wah! And he's like, Mr. E, let's go up to Whistler. We'll have a refreshment or something up there. I'm like, okay, let's go. I'll meet you up there. I'm gonna drive my old dented truck, and you drive your Alfa. So Ethan's like, he obeys the law, okay, because we're on video here. And he's boom up to Whistler, and he gets there in an hour, and it takes me 2 hours to drive in my car. Who did more work, Ethan or me? Parham? It's about the same. It's about the same. Because we went the same distance, probably friction's about the same, or, you know. But who was more powerful? Ethan's Alfa Romeo is much more powerful than my truck. Because I'm just like, you know, and he's like, right? So he does the work in a smaller amount of time. So there's more power. So power is the rate of doing work. So work is transforming energy, right? It's not creating energy, it's not using up the energy, but it's transforming from one form into another form. Gavin, I think you're making a nice bell there. It was kind of rhythmic. So work and energy don't care about time. Power is measured in joules per second, which is a watt. And you can see this formula, it's up there. P, it's kind of faded, this one. I need to darken it in, but it's P equals W over T. So work over time, or the change in energy over time. And that is watts.
So joules per second is equivalent to watts.
That is correct.
So it doesn't matter which one you rate.
Nope. If you write a W for watts, I'll be good. Or if you want to write J per S, that'll be good too. Make sense?
Yeah.
Watts. Watts. Okay, try to do this problem. Asti, how am I gonna do this? What do I need to find out? We're looking for power.
So work.
So yeah, that's right, Malika. We need to find the work that she does, and then we can divide it by the time, right? She's doing work. When you walk up a set of stairs, what kind of energy are you gaining as you go up the stairs?
You're gaining potential.
Good. You're gaining potential energy. So at the top, what's her potential energy that she has at the top?
2.8.
I'm going to say EPF for final potential energy. Say that again, Parham.
What was it? 60 times 9.8 times. What was the height? 2.4.
Good.
2.5.
So, Hasti, what's the formula?
MGH.
Yeah, good. So you're going to do MGH. And in this case, she's 60 kilograms. And the G is 9.8. Do you want 9.8 or 10? 10? Okay, let's do G as 10. Because we're lazy. That's why. So we do 60 times 10, and the height is 2.5. So that's 600 times 2.5, which is 1,200, and 300, which is 1,500. So she's gaining potential energy, right?
What's EPS stand for?
Potential energy final. So at the end, she's got this many joules that she saved up. Now that's the potential energy at the top. It's also the amount of work that she would have had to do to move up that height.
So is it distance?
Well, do you need that?
No.
All we want is power, right? So this is also my work. It's my potential energy at the end, but it's also the work that she had to do to gain that potential energy.
333 watts.
I think that's right, Sarush.
0.3, repeating.
So this is 1,500 joules, and it took her 4.5 seconds.
333.3 repeat.
330 joules per second, which equals 333 watts, and that's my power. Okay.
What is joules? What is second?
Joules per second and watts are the same thing. Malika.
Wait, sorry, how did you do that? Oh, you divided it by the time?
Yeah,
Yeah.
yeah. So we took the work she did, divided by the time, and we get her power. Now that's the power that she got out. We're going to talk about the difference between the power you get out and the power you get in. What's the point of walking up a staircase?
Somewhere
To get up.
When you're down in the cafeteria, to get up here, you have to walk up the staircase, right? Why are you walking up the staircase?
To get
To get to
somewhere?
class.
Yeah, to get to class, and the class is a floor above the caf, right? So
Day
that's
night.
the energy that's what you get out of walking up the stairs. We get out that. Now, some of you are thinking a little bit and you're like, yeah, sure, Mr. E, but she's walking up the stairs, which means she's making sound and she's like, oh, and she's sweating and she's like making heat and there's friction on the floor, it's messy. She's burning way more than this. Like, yeah, that's her potential energy. But is that the energy that she would have put in to get up the stairs? Or would she have had to put more in? Or would she put in less energy? She gets 1,500 joules of potential, right? So do you think she burned exactly 1,500 joules, like in real life?
No.
No. Would it be more or less?
More.
Tell me why more, Sarush. You are correct.
Because they're doing extra things.
Yeah, she's doing all the extra stuff, right? When we walk around, we're burning energy, we're creating heat, and we got friction, we're making sound and light and all kinds of other things, right? So she would have had to put more than 1,500 joules in, because the process is not 100% efficient. Good part. But we're gonna learn a little bit more about that later. Okay. Try this one. I'll post this video if you want to see this later too.
Put it in scientific notation.
This is 1,000.
Yes.
So you have a 1,000 kilogram car, accelerates from rest, and it gets up to a velocity of 15 meters per second in 4 seconds. So we want to calculate the power output of the car. Now your brain might click into kinematics here because we have a VI equals 0, and we have a VF, and we have a time, and so we could find the acceleration and the net force and all that stuff. But we don't need to do that here. Much simpler. With a car, what type of energy are we getting out of this?
Kinetic.
Kinetic. We want the car to move, right? That's the purpose of the car. So, Cheyenne, what's the formula for kinetic energy?
Half of time.
Good. We could say VF, right? How much kinetic energy is there when we start?
0.
0. We're not moving in the beginning, so we got 0. So this is going to tell us all the energy we have gained. So let's do that. It's 1,000 kilograms, and we get up to 15 meters per second. And 15 squared is 225. Keanu told me that this morning. And 225 times 1,000 would be 225,000, but it's half of that, so 112.5, I think.
Let's double.
Is that right? Or is there one less 0? Is it right? What's the unit of this?
Good job.
It's good. What's the unit of this?
Joules.
Joules. Thank you, Owen. This is energy, so this is going to be in joules. This is the amount of work that the car had to do, right? It's the amount of energy we're getting out. Okay, so how are we going to turn that energy into power?
Use time.
Good. Power is going to equal our change in energy over time, we could say. It's work over time, but that's the same as the energy change.
Calculate potential energy too.
Are we changing potential energy? Is the car going up a hill or down a hill?
What does the potential energy equal
Yeah.
to it?
Yeah. So there's no change in potential energy. Not gravitationally, at least. So we're really just gaining kinetic. So we can put our change in kinetic here and divide by our time, which is 4 seconds.
Oh wait, it says the time.
Yeah, it already says the time, yeah.
I didn't see that.
On a test, I probably would make it more complicated. I'd make you find the time, but
How much more time?
well, I'd have to give you like the acceleration or something like that.
How would you do that?
You would have to have acceleration or else you couldn't do that.
This is 25,000 and 3,000, so 28,125.
Yeah.
And that's in watts. That's a really high wattage. That's very powerful. It's a fast car. And this is like 55 like kilometers per hour in 4 seconds. That's pretty fast. So that's a fast car and it's very powerful. 28,000 watts. Your blender at home is probably 200 or 300 watts. My e-bike is 1,000 watts. So this is like 28,000 times more powerful than my e-bike. Yours is 6,000? You should not have said that on video. They're gonna use it as evidence. They're gonna come get you. You be careful with that. Is it really 6,000? How fast does it go?
Does it go
30 kilometers per hour.
Yeah, right. Mine goes faster than that. Is it like seriously? How fast have you gone?
I can show you.
I don't want to see it. You're gonna die. That's gonna be careful. You need to be careful with that. That's a lot of power, man. That's a lot of power. Okay, one other thing here. It's kind of a quick lesson, hopefully. Work is force times distance, right? So if work is force times distance, then you could say FD over T would be power, right? What is D over T?
Distance over
Yeah, what's distance over time? What is that? It's velocity, right? Thank you, Anna. So if that's V, then you can say that power would equal force times velocity. And that's a handy little formula. But this only works in one situation. It only works when the velocity is constant.
Oh yeah, I was gonna ask, in the other formula, can you use like the formula with velocity? Like, is that initial velocity or like final?
Which formula?
The mv, the 1/2 mv squared.
Oh, well, when you're finding power, you want to find the change in energy. So it depends on the situation. Like if something is, say I give something a velocity, say I slide it, and then it slides to a stop, and you want to find the work that friction did, bless you, then you do the 1/2 mv squared at the beginning, and you minus 0, and so that's the difference. But if it's a car where you're sitting still and then you hit the gas,
But what if it's already moving and then it accelerates?
okay, so then you want to find the 1/2 mv squared at the end,
So velocity.
and subtract the 1/2 mv squared from the beginning.
So like the change in velocity.
Yeah.
So basically it'll always be just like one velocity because either it starts from rest and then accelerates to, or then goes to velocity final.
Well, we could do a problem like say your car starts at 10 meters per second and goes to 30. You would have to do 1/2 m,
Would it just be 20 meters per second squared?
yeah, because you're gaining 20. It's the change. It's the change in velocity. There's one little problem. So this works. It's handy. It's not on the wall because I don't want you to get confused and think you can just throw a velocity in there and multiply by the force. This only works when your velocity is constant. So here's an example. Try to do that one. So can we use that formula here? Daniel's nodding his head. We can use it here because it's a constant velocity. Now, again, this is kind of the same as work. Which force is this? Would it be the net force?
Would it be
Yeah.
FA?
Correct. Good job, Malika. It's not net force because the net force here is 0, right?
So should we just write FAV?
So power is my fave.
Applied force.
Yeah, it's applied force.
So in this case, it
Could
would
it
be
never
140.
be FNet? Like never?
No, never, because when you're on a constant, you're at a constant velocity,
Oh,
net force is
FNet's
0.
How about that?
So it's got to be the FA. Now, if you're looking for the power that friction is like exerting, then you would do this FF. But in this case, your applied force and the friction force are the same thing.
Yeah, but then it wouldn't be moving. Like if the
It's
friction-
moving, but it's not accelerating.
But. Okay, yeah, true. So you could-
Actually, sorry, I said that your applied force and friction force would be the same, but they wouldn't be because you're going against gravity up
Yeah,
or
because
down.
the friction force would have to be the same as applied force.
Yeah,
And then,
you'd have gravity kind of pulling you downhill and you pushing uphill and also a little bit of friction. But it doesn't really matter.
wait, but is this for slope?
This is up a slope, yeah.
Why are we talking, oh.
This is up a ramp. So like your box would be here and then. But this kind of doesn't really matter. You just need your power at a constant velocity will be your applied force times the.
So
The
when,
ramp
like,
is
when would you use
irrelevant.
FF?
The ramp is kind of irrelevant, yeah, it doesn't really matter what else is happening.
In this case, it gives you the FA, but if it didn't give you the FA, then it would be mass times like A to find it.
That would be your net force.
Oh, and
Should- Would it be like mass times like?
We're gonna do that next. We're gonna do that next. So this is simple. Your applied force is 140, and you're gonna multiply it by 2.2, and that's gonna be 280 and 28, so 308, I think. And that's watts. Yeah, shine it. Put your hand if you got 308. Yay, good.
No.
Okay, one more.
When would you use the FFE? That's what I really wanna know.
Oh, listen.
Well, Kurt, could you get
Do you want to do a friction one?
like, I just wanna do one where you would use FFV.
FFE?
So you said you can use FA or FF.
Okay, let's do one right now. It's a good question. So let's say, what do you want me to slide on the floor?
A pomegranate.
Oh, man, I love it.
Is that your
Uh,
pomegranate?
Yeah, that's my best pomegranate. The pomegranate is it's gonna start with a VI of 12 meters per second. And it's gonna go to 0. And how long? Do you want me to give you time or distance?
10 minutes?
Distance.
10 seconds?
Because I feel like you would give us distance on like a test or something.
Let's say time is 10 seconds. So tell me the power that friction exerts on the pomegranate. You actually don't have to do any kinematics. You can just do it with energy.
At 10 times.
Oh, this is not a FFV one. Sorry, do you want the FFV
No,
one?
it's fine. Let's just do this one because we're already.
Because we're already here? Okay.
Can we do the other one next though?
Sure. So this one is going to be delta EK, right? Over time will be your power. Because the friction's taking away the speed.
Where's that from?
So would it be negative?
This is the work. This is the work that friction is doing. Friction slows things down, right?
So would it be negative answer?
So you do the decrease in the kinetic energy when you're working with friction. So you find the EK at the beginning. How much EK do you have at the end? None. So you just find your EK at the beginning, that's your work, and you divide by the time. Oh, I didn't tell you the mass.
Of the pop-up again. Yeah,
Let's say a 3 kilogram pomegranate.
okay, that's a big pomegranate.
Yeah, I really like big juicy pomegranates.
I can do it.
So let's say half mv squared over t. So that's half of 3 times 12. 144 times 1.5 is 72. So 212. Oops. Is that 212? Over 10. Is that right?
How do people even like figure this out? Like, who was the first person that came up with this and was like, yes.
Half mv squared?
So many.
Just all of this. Like, it makes no sense.
Isaac Newton was the first. Well, no, he wasn't the first. It actually took a lot of people in a long time.
Yeah.
Yeah. Yeah, and then you get into what I teach my IBs. You find out that this is only like a small part of it. Yes, Malika.
You know how like all the scientists, like they all have like a photo of themselves? Like I heard that Robert Hooke never had like an actual photo.
He did, but Isaac Newton burned them all because he hated Robert Hooke. It's like
That's great. Such a hater.
he was a hater. Newton was a real hater. Weirdo too.
Haters back then too. It's not a new phenomenon.
Isaac Newton wrote in his memoirs that he suffered from visions of him burning his mother in her bed. Yeah, he said that. He never did it, but he said that he had those visions. And he spent a lot of time trying to decipher secret messages out of the Bible. He thought the answer to life would be in there somewhere. But he never made it. He never got anywhere. But he did figure out a lot of stuff. Was that right? Is this correct?
All of this was his side
Yeah,
quest.
thank you, Malika. So this is gonna be the watts, and this is the work that friction did. It's kind of a weird situation with friction because it's slowing things down, right? But here's a question: this pomegranate slides to a stop, right? But the kinetic energy is going to 0. So where does that energy go? Where is it? Heat. Friction takes kinetic energy, turns it into heat. So this 212 joules, that's how much kinetic energy we lost. How many joules of heat would be in this surface here? 212 joules of
I'm a bit confused.
heat. Tell me, Ollie.
It's overwhelmed with so many steps.
Okay, think about this. Let's say we're on a frictionless road. You have a perfect car, no friction. You hit the gas and you go, vroom, and you get 100 joules of kinetic energy, and everything is perfect. That means that you put 100 joules of energy in from the gasoline, and you get 100 joules of kinetic energy. Okay. In the real world, though, the car is at best 50% efficient. So if I gain 100 joules of kinetic energy, I actually had to use 200 joules of gasoline. What happened to the rest of that energy? A little bit of sound, mostly heat. Heat. You get that?
So
Okay.
the EP and
We're gonna talk
are
more
the
about that.
same?
The EP stays the same because it's not going
Wait, so
over.
is it 100 EP and 100 EK? If in the scenario you just described?
If the car is perfect, yes, but that's chemical
I don't
energy.
understand this.
I don't understand this. Reza?
Yes.
Go ahead.
Or only use 16% of
Oh wait, no, I get it.
the gas
Power.
energy, and the cells only use, I think, 32% of energy they can use. And
Okay.
it's a huge energy, the heat.
Yes. The heat is the enemy of every engineer. Okay, if you're building a car or a plane or a fan or a tea kettle, no, not a tea kettle because we want heat out of the tea kettle. But everything that you build, you want to reduce friction because you don't want your, like a light bulb, for example, you do not want your light bulb making heat. You want it making light, right? But friction does do work and it does create heat. And in this case, it takes all the kinetic energy from the sliding thing and it turns it all into heat.
Is the like force applied, like the power of the force, not the same as like the power of the friction?
In this case, it is. Your friction is the applied force if you're figuring out the power of friction.
But in like the other one, wouldn't it have been the same too?
Thank you for bringing that up. Juder,
Yeah.
this is your FV scenario. Let's do one of these. Let's say I'm pushing the pomegranate at a constant velocity, okay? I just keep pushing it, and it's 3 meters per second, okay? And I have to push with, how many newtons? 4 newtons?
How do you figure that out?
So my F applied equals 4 newtons. And if I just keep pushing it, like it's like something with friction. If I push my coffee cup with 4 newtons
Where's the 4 newtons?
at a constant velocity,
He's just giving us.
I'm just telling you. I'm just making it up.
Okay, I was like,
I'm just making up 4 newtons. But it's not accelerating and it's not slowing down. So this is moving at a constant velocity. That's right.
so that means the force of friction is also 4 newtons.
So what's the power that I'm exerting?
12 watts.
Good. Malika, gold star for you. For this one, I can just do power equals force times velocity.
Oh yeah, it's just 4 times 3.
And it's just my 4 newtons times my 3 meters per second, and that will give me 12 watts. Now this is kind of interesting because if I'm pushing it, why is it not speeding up? Because, Parham? Friction. So every second, I'm putting 12 joules in. So long as I keep pushing it. In 1 second, 12 joules. Another second, 12 joules. Another second, 12 joules. Another second, 12 joules. Every second, I'm putting in 12 joules. What's happening to that 12 joules? Where's it going? Because I'm not speeding up. I'm just staying the same. Heat. Good, Malika. You're on fire today. Let's give her a golf cup. So every second that I go here, if I just keep on going, every second I'm losing 12 joules of heat. And I go another second, and I lose 12 joules of heat. And I go another second, and I lose 12 joules of heat. And so my power is 12 joules per second. That's what I have to put in because I'm losing 12 joules of heat every second. So just to keep it the same velocity, I have to put in 12 joules. Yes?
Are joules and watts like interchangeable and are they always the same?
They're not interchangeable. So let's say I push this thing for 3 seconds. How much energy do I use?
30.
Yes. Because every second I burn 12 and 12 and 12. So at the end of 3 seconds, I would have put in 36 joules of energy, and there would be 36 joules of heat energy here. But my power would be 12 watts. Because every second I use only 12 joules. So the watts is like joules per second. It's kind of like speed and distance. Energy is like the distance, and power is like the speed. Speed of the energy
The height
being
of it.
changed.
Should like all run up the stairs.
Does that make sense? Kind of, sort of.
Measure endless
Maybe.
time.
Okay. I'm gonna give you some little problems to do. I'm gonna give you a little break. I'll shut this video off, and then we're gonna learn about efficiency in a minute.